Hello and welcome to this Unisensor microsensor lecture. My name is Lars Hauer Larsen and I am CSO here at Unisense and responsible for production and development of Unisense microsensors. In this presentation I will give you an introduction to how our oxygen microsensors are designed and working, which will hopefully familiarize with them and help you applying them correctly. The Unisense oxygen microsensor is of the amperometric microsensor type, also known as Clark type sensors, and an in-depth lecture about the working principles for these sensor types is available on our website. In this lecture I will focus especially on the oxygen microsensor and its performance. It will cover the following topics: the chip design and the detection principle. I will give some comments to the specifications of the sensor. I will explain how our needle sensors is produced, and at last I will turn to how to troubleshoot. Here is a photo of an oxygen sensor and a photo of an oxygen sensor in action. Details and general theory about Unisense amperometric microsensors are covered in the lecture about Unisense amperometric microsensors, but I will here briefly describe the chip design and the working principle. The outer tapered glass casing is equipped with a silicon chip membrane. The function of the membrane is to make a barrier between the electrochemistry inside the microsensor and the sample. The membrane is permeable to oxygen. If oxygen is present, it diffuses through the membrane to the working electrode. The working electrode surface is a negatively polarized gold electrode, which catalyzes reduction of oxygen. The electrons for the reduction are delivered from a silver chloride reference electrode 10 to 15 centimeter away from the working electrode. But for sake of illustrating the principles, it is included in the schematic drawing of the sensor chip. The current generated is proportional to the concentration of oxygen outside the chip membrane, and as the current is very small, the picoamp range, a high quality amperemeter is necessary for amplifying such tiny current. The guard electrode reduces oxygen dissolved in the electrolyte, which would otherwise react on the working electrode for keeping the baseline low. The cavity is filled with an alkaline aqueous electrolyte, which ensures electrical connection between the electrodes and ensures charge balance. The anionic and cathodic reactions is shown for the sensor. Oxygen is in two steps reduced to OX- ions on the working electrode, and the electrons are supplied by oxidizing silver atoms to silver ions on the reference electrode. The silver ions are precipitated with chloride, which is present in the electrolyte, so the half-cell potential of the reference electrode is kept stable. I will now turn to the actual performance and specs of the oxygen sensors and give some comments to them. Recall that these specs are only guaranteed with use of a Unisense meter. The detection limit is stated to be 0.3 micromolar dissolved oxygen. However, the detection limit is in practice strongly influenced by the application in question. By producing the oxygen sensors with a larger chip membrane, the sensors can be made more sensitive with a detection limit down to 15 nanomolar. The detection limit will, however, affect the response time and steering sensitivity. The response time will be slow, however, in order to prevent high steering sensitivity. For detection of oxygen within the low nanomolar range, a STOX sensor should be used. The chip size ranges from 10 to 500 micrometers. We produce them in standard models with 10, 25, 50, 100, 200 and 500 micrometers. We can, however, make them with chips down to 3 to 5 micrometer. Naturally, the smaller the chip is, the more fragile it will be. Larger sensors are made with thick glass walls, making them quite robust for profiling in matrices. Consult our guide for chip selection for more information. We can custom-made the chip design regarding slenderness and modify the sensor body if requested. The response time is a function of the oxygen diffusion path lengths into the working electrode and is chosen to obtain the best compromise between sensitivity, response time and steering sensitivity. Small sensors are made with shorter response time than larger, but all have below 10-second response times. Details on response times is found in the oxygen sensor specification on our website. Oxygen sensors can be custom made with short membranes to shorten the diffusion distance, and thus oxygen sensors can be made very fast, down to 0.3 seconds for a 90% response time. Oxygen sensors respond linearly to oxygen concentrations. They respond linear up to above 100% oxygen saturation, and even in supersaturated water or pressurized oxygen gas, the sensor responds linearly. The oxygen sensors can be applied with a spatial resolution which equals the tip diameter. This is just a rule of thumb because it cannot easily be validated. The sensor will sample oxygen from a very minute diffusion sphere at the membrane/sample interface. But physical disturbance, which increase with tip size, should also be considered when profiling in biologically active matrices. The sensitivity to stirring is for standard sensors less than 2%. The sensitivity to stirring is defined as the difference between the signal in stirred and stagnant sample with the same oxygen concentration. This is exemplified here, where a sensor measures in a continuously mixed sample. When the stirring is stopped, the signal decreases about 1%, which is typical for an oxygen sensor. And when the stirring is reactivated, the signal is back to the original level. The lifetime is long if they are not physically damaged. Oxygen microsensors can last for years. The signal generated by the sensor is so small that the electrolyte and reference capacity will never end out. Thus, the lifetime is not influenced by how much it is used. The signal stability increases with time. The diffusion coefficient through membrane and electrolyte settles over time, and as the lifetime is very long, the drift after some time is minimal. As the sensors are handmade, the drift vary among the oxygen sensors, exemplified here with 3 oxygen sensors starting with the same sensitivity, but after some time the signals are different. Thus, it cannot be predicted precisely how much drift a user will experience. We recommend calibrating whenever possible and convenient for all important measurements. The baseline does not change significantly with time. Physical impact on the sensor can, besides destroying the sensor, change the sensitivity and thereby the calibration of an oxygen microsensor. The working electrode connects to the amperemeter via a thin, flexible glass covered platinum wire. Physical impact, which shocks the internal components, can induce a displacement of the working electrode position relative to the membrane, and thereby changing the sensitivity. Typically, such impact will induce a sudden signal peak followed by a stabilization time, but the sensitivity might not return to the original sensitivity due to a displacement of the working electrode position. Oxygen sensors stand up to 5 times atmospheric pressure without being pressure compensated. However, like other Unisense microsensors and electrodes, we can pressure compensate the inner parts of the sensor so they can withstand full oceanic pressure. When pressure compensated, they are tested to be able to withstand 600 bars. This photo shows an oxygen sensor mounted in an Unisense in situ amplifier where an oil-filled membrane equilibrates in situ pressure with electrolyte. In the web lecture about amperemetric microsensors, the temperature influence is discussed in detail, and it is explained why temperature compensation is difficult for amperemetric microsensors. The temperature interference is about 2% per degree. For sensors used with the new Unisense UniAmp portfolio, temperature is compensated for within ±3 degrees Celsius interval. The sensors can be used from -10 to 60 degrees Celsius. For applications at higher temperatures, we produce sensors with organic electrolyte, which can stand higher temperatures. I will not in this presentation go into details with all the adaptations and modifications we can do to the oxygen sensor. This is covered in the quick guide. But I would at this point describe how a needle-embedded sensor is made. We make needle-embedded versions of the oxygen sensors in order to give some protection to the sensor tip from being damaged. We make them in two different versions, OX-N and OX-NP. The latter is made for piercing membranes. This is a schematic drawing of the tip of OX-N and OX-NP sensors. The needle protects to some extent the glass, but the sensor tip is still fully exposed to the sample solution. The needle and the glass part of the sensor is glued together inside the needle, so no sample liquid will intrude into the needle. This would otherwise cause a huge carryover effect. I will now turn to troubleshooting oxygen microsensors which do not exhibit normal performance. Naturally, small glass tip sensors are fragile, and the tip might break if it hits something hard. This is a photo of an intact OX-10 sensor, and to the right a photo of the same sensor is shown, but now with a broken tip. It is seen how the working electrode is exposed as the glass tip is missing. A broken sensor will in water give a very high signal, typically out of range, as the working electrode is now directly exposed to the sample. So, if the tip breaks during measurements, a sharp signal rise will occur to the out-of-range level. Sometimes the sensor does still respond to oxygen because the exposed working electrode can still produce oxygen, but it will be very unstable. It is not possible to repair a broken sensor. If the sensor tip gets biofouled or covered with sticky polymers, it might measure incorrectly. The sensor tip tolerates almost all possible cleaning substances like alcohols, acid, detergents, proteinases, etc. So it is recommended to insert the sensor in different cleaning substances or solutions to see if this solves the problem as the first attempt to remove the fouling. We do sometimes see that sensors used in protein-rich sample like blood, the sensors lose their oxygen sensitivity when dry, but restore the sensitivity again in water or wet samples. This is due to a protein cover which, when dry, prevents oxygen to diffuse into the membrane. In water or humid air, the polymer cover swells and becomes oxygen permeable. If chemical cleaning does not remove the fouling and restore normal performance of the sensor, a physical cleaning is the only solution. For OX-50 and larger sensors, it is safe to wipe the membrane with a piece of soft, wetted fabric or paper. If you hold the sensor so the tip points away from you, the wipe direction must always be the direction the tip points, never against the tip, which will impose a risk of tip damage. For OX-25 and OX-10 sensors, physically wiping might break the tip. For physical cleaning of these fragile sensors, we recommend that you hook the electrode up in a microprofiling system and gently insert the sensor into a soft matrix, which gives some shear force on the fouling material and removes it. The best material we know of to do this is the Oasis flower foam. It should be wetted before inserting the sensor. For customers using 3 to 5 micrometer sensors, we recommend to profile in agar or agarose gel to remove fouling. These curves illustrate a normal startup behavior of an oxygen microsensor when connected to a Unisense amplifier. The signal is high and downward drifting right after connection due to reduction of electrolyte dissolved oxygen, which are slowly removed by the guard electrode. If there is not such an initial peak signal, but instead the signal does not rise much from zero, it might be due to a gas bubble stuck in the tip which disconnect the working electrode from the reference. There must be an air/gas phase in the electrolyte cavity in order to make room for temperature-induced expansion of the electrolyte. And if the sensor package was turned upside down during shipment, a gas bubble can be trapped in the tip. Such air bubble can be removed by shaking the sensor like demonstrated here. The bubble will become loose and rise to the top of the electrolyte, and connections will be restored. In rare cases, a gas phase can evolve in the tip at the position of the working electrode, and such gas cannot be removed by shaking. So if there is no signal from the sensor, this could potentially be an explanation. Such gas phase can easily be removed by inserting the tip into degassed water, which will drag the gas out of the tip through the membrane. Fill water into a glass bottle and boil the water. This drags gases out of the water. Let the water cool to room temperature or below without shaking the bottle or mixing the water. Place the sensor tip into the water for some hours. The gas will be removed by this procedure. If a sensor experiences a physical impact, like a drop on the table, the working electrode could be displaced. If the displacements result in a working electrode retraction from the silicon membrane, the signal will be slow and sensitivity low. The sensor will still work, but have lost its original performance. It is unfortunately not possible to restore original performance. A physical impact, like a drop, could also damage the glass insulation of the platinum wire which connects to the working electrode. This will typically result in an elevated and noisy baseline signal due to exposure of polarized platinum surface to the electrolyte. Chemical reactions taking place on the exposed platinum surface will create a current which will overlay the working electrode generated current. The size of the baseline increase will depend on the degree of damage to the platinum wire insulation. Such damages cannot be repaired. Fast responding oxygen sensors have a very short membrane which can be vulnerable to electrostatic discharges. A charged person who touches, for example, a beaker in which the sensor tip is placed can induce a potential difference of thousands of volts across the membrane and potentially induce a discharge which destroys the membrane. To be sure that this does not happen, a grounding wire should be connected to the liquid or setup in which the sensor tip is placed to the ground socket of the Unisense amplifier. A sensor with a damaged tip membrane will have a very unstable signal, strongly affected by electrical noise. By grounding the sample or experiment to the ground socket of the amplifier, the signal will stabilize. A damaged membrane cannot be repaired. Thank you for watching this Unisense microsensor lecture. I hope you enjoyed it. If you have any questions, you are more than welcome to contact us at sales@unisense.com.